Good morning, everybody. Welcome back. And we are moving on to the biochemistry portion of this course, the final portion of this course. And I'm looking forward to exploring that with you right now. We've got some bad news. It's not really bad. And we've got some good news. We don't have any more textbook for this course. We will be relying solely on the available notes at HFC Online Moodle. And the good news is students almost always do better on test 4 than other exams, and they comment often that it's more like a biology exam with some organic chemistry mixed in, and that's true. All the learning you've been doing so far is to get you to this point where we can understand how biological molecules do the same thing as the organic molecules we've been studying for, 2 semesters now. Our big goal today is to get into some naming of sugars. Chapter 25 is what we're starting now, which is called Carbohydrates. Chapter 25. Carbohydrates. An interesting name all by itself, in that the simplest carbohydrates have that name because their formula is CN and water taken N times as well. And a lot of you have had some biology, and you think of molecules like glucose, that's C6H12O6. And if you want to break that down into how many carbons and how many waters, the answer is 6. C6 water 6 times. So that's where the word carbohydrate comes from. It has nothing to do with the chemistry of hydrates of carbon. You've studied hydrates in inorganic chemistry, and they are molecules that can easily lose their water, and carbohydrates don't like doing that typically, although you can make them lose water. In fact, we're going to make this lose water when it condenses with adenine here in a review reaction. Over here's our goal for the end of the day, is to be able to name disaccharides and monosaccharides for that matter. We'll start with monosaccharides. And we have to use some resources that are available to us for our exam. But right now, let's do a review mechanism with a little new, I wouldn't even call it a twist. In biology, we're going to talk about HNs with a plus charge being the protonated version of an active site of a protein. And it represents the acid catalyst, and the conjugate base would be N's with its lone pair. N's short for enzyme. And the mechanisms are not going to change from what we did before. I want to remind you that you're taking an aldehyde and you're making it into a hemiacetal here. Hemiacetal, how do I know it's a hemiacetal? Hemiacetal has a special carbon right here. And that's the same carbon here. And that used to be this carbon over here. And in the scheme up here, aldehyde is in equilibrium with hemiacetal, is in equilibrium with N-acetal. It's like an acetal, but nitrogen took the place of an oxygen. And this carbon all the way through here at the end has a special name. Special name. And for carbohydrates, the hemiacetal carbon or the acetal carbon is called the anomeric carbon. And you can identify it quite easily. It used to be the one with 2 bonds to oxygen that used to be a carbonyl. It still has 2 bonds to oxygen here, alcohol and ether simultaneously. That's what we learned in chapter 16, is called a hemiacetal. And here it's an N-acetal, and it's the anomeric carbon has a bond to oxygen in an ether and an amine. If it was a diether, we just call it a normal old acetal. And this is all review, nothing new here. We're going to use red arrows first for our mechanism. And we're going to go with baby blue second. And keep in mind the molecules you'll be drawing for this last portion of the course tend to get a little larger because, you know, they're real, and we want to avoid drawing as much as we can. First step would be to activate the carbonyl using the protonated enzyme. Second step, clearly an oxygen carbon bond needs to happen. And what I'm going to do is do a little editing here. Show that H off of here. Here's the lone pair. Second step, lone pair attacks the activated carbonyl carbon. And we can actually finish the mechanism off. This second arrow would have generated an oxonium on this position here, this oxygen, and the enzyme will take care of that in a third step. Enzyme lone pair neutralizes the oxonium. And we go straight to our hemiacetal. Now we need a new activated carbonyl. How do we obtain that? Well, we have to make the oxygen a better leaving group. Clearly this oxygen's got to go. It's the one that ends up over here. There's the oxygen. Protonate it to make a better leaving group. Kick it off with the lone pair on the oxygen over here in the hemiacetal. Second step. So the water's gone and you have an activated carbonyl, which we do have to draw. This arrow's a little bit unclear. There, definitely a pi. So we have an equilibrium step here. Hemiacetal. And we're generating this species here. Have an OH up there on a CH2. We have a downwards OH here. And that's it for that. Lost some water, and we have a plus charge. That's an activated carbonyl. An amine nucleophile, even a poor one like that found in adenine. And you say, okay, adenine's using a lone pair for resonance in an aromatic ring. It's not going to be very happy about this, and you would be correct. This being use the lone pair on the nitrogen. The nitrogen here is going to attack the activated carbonyl. And I don't want to have to draw that too many times. We can, if we're clear with our short forms, we can do good things. I'm going to try to indicate everything up to the NH. And you're saying, wait, how are you going to have the N there? I'll show you. We're going to attack that carbonyl, generating our N-acetal, but it'll be an ammonium ion that desperately wants to become aromatic again. Get its lone pair back. We'll account for that. And that's going to go Got some strange looking equilibrium arrow here. And what's going to happen? I don't even know if I needed the R short form, did I? I'll explain it later. Because I'm not going to be drawing an intermediate, my enzyme is going to take that H to finish this thing off. Enzyme will take the ammonium H. This would be a second step. You generated an ammonium, and now you neutralized it. And I don't want it to be unclear here, so I'm just going to get rid of that. Didn't need it. And that. And that's how you can generate an N-acetal and a hemiacetal using monosaccharides like 2-deoxy-D-ribose. We have to explain this name too. We're going to introduce naming right now. So let's start while we're here. Normally, ribose has another OH on this carbon number 2. The numbering is aldehyde is 1, 1, 2, 3, 4, 5. It's a 5 carbon sugar. C5H10O5. So it works it down here too. But now it's lost its oxygen. That's why it's got 2-deoxy in its name. And this is the form of ribose used to make DNA. The D standing for deoxy. That word right there. The D does not stand for D-ribose. It's understood we use D-ribose. We'll talk about what the D there means. And it means it's a natural sugar. We'll have a whole handout of natural sugars showing up on the next page. Okay. And the naming, when we go from the open form, I say open form because there's no ring here. It's the Fisher form, but it's been looped around. We'll review Fisher forms very shortly. And this has a different ending to its name. Furan has a meaning based on this species right here named furan, which we studied earlier on our last test. Furan. And if a ring has that ring size, it's a furanose. So these are just reference molecules. They're not carbohydrates. References. And we have another molecule with a ring size 6. And it's here, and it's called pyran. So when a sugar adopts ring size 6 with an oxygen in one of the corners, it's called a pyranose, not a furanose. Furanose is for 5. That's the easier one to remember, isn't it? Furanose, ring size 5. Don't forget one of those atoms in the ring is an oxygen. Pyran is the ring size 6. So in our molecule for the end of the day, there's a pyran in here. Look at ring size 6. 1, 2, 3, 4, 5, 6. Ring size 5 down here. A furanose down here. 1, 2, 3, 4, 5. A little preview. We'll finish this segment by looking at a handout that is available to us for test 4. Do not memorize this handout. That pleasure will be given to you by your first biochemistry instructor, who will make you memorize this handout. I'm pretty sure most of them do. And you'll come up with lots of cute memory tricks, I'm sure. But we're not going to memorize it. Now, there's 2 major types of sugars on this handout called the monosaccharides. By the way, all of these on this page, all are CNH2O. And everything here fits that. That is the formula for monosaccharides. That is carbohydrates. On the left side of the page, we have aldehydes. Aldehyde sugars are called aldoses. On the right side of the page, we have ketones. Sugars that have ketone functional groups are called ketoses, and their derivatives are also called ketoses. Over here, we have the simplest aldose. It's an aldotriose. And the simplest possible ketose is over here, ketotriose. These are classifications. I think you know what the keto means. There's a ketone in it. I think you can figure out what the triose means. 3 carbons. Same for the aldotriose. There's an aldehyde on top and 3 carbons. Down here are the very popular aldohexoses. All of the ones on the bottom. And I see how many? 2, 4, 6, 8. Now, keeping in mind there's 4 stereocenters, possible isomers would be 2 to the power of 4, which is not 8, but 16. So why are they only 8 here? Well, the answer is these are all the D sugars. Notice the name in front of every sugar save one on this page. Every name has a D in front. And where is that sugar that doesn't have the D in front? It's this one right here. Why is there no D in front? Well, as promised, I will explain what the D means. Every sugar that has a D in front has this in common. We'll go to our friend D-glucose here as one example, but I could have done this on every sugar that has D in the name. I circle the stereocenter that's closest to the bottom. I circle its number 1 priority group, which is an O, and it's to the right. And if you're French, that's easy to remember. It's à droite with a D. Now look over here. There's OH here on the right, on the last stereocenter down. Over here on the right, on the last stereocenter down. None of the other stereocenters are relevant for this D. It's only the last stereocenter down. Down away from the carbonyl is what I should say. Dihydroxyacetone does not have a stereocenter. There's no need to say that the last stereocenter has the OH on the right side. There is no OH. There is no stereocenter. So there you go. Brief explanation of all of the monosaccharides. And please, you have to use this handout multiple times on the test. Get a nice clean printout for yourself and use it as you're doing any practice problems. Okay, so let's look ahead and then take a break after we see what's ahead. I hope it's clear here. I stole this right from section 13 carbohydrate notes. That's Moodle section 13. And it's got the rundown on how to go from a Fischer form. These are Fischers. I want to remind you, because I don't think your section did a great deal of details on Fischers. But Fischer does stereocenters like this. And it's a time saver. Whenever you see that, there's a carbon there. And we have wedges on the horizontal. Don't invent your own Fischer system. And we have dashes on the vertical. And this is very easy to remember. This is very easy to remember. Is our video still going? I hope it's still going. I have some weird things showing on my screen. I apologize. Yeah, horizontal looks like a bow tie, and vertical looks like a zipper. Remember that. Bow ties and zippers. A bow tie, like a formal dress wear, is worn horizontally, and it looks like two wedges, and a zipper is vertical, and it looks like two dashes. And we have fissures for all of our stereocenters here. You can see how much time it would have taken if we had to draw wedge for all the horizontal bonds, left-right bonds, and dash for all the vertical bonds. The shape is very important. Fisher came up with this short form. I want to point out Fisher's short form predated the people who named stereocenters, Conning-Gold and Prelog. So all of the H's are always on wedges. Don't blame Mr. Fisher. He just came up with a nice short form. If you want to do R and S, remember a wedge is not where it should be. The H should be on a dash. Oh, but that's just as easy as being on a dash, isn't it? Do the circle and your answer's wrong. So give me the right answer. A lot going on there. You can read about Fisher projections in chapter 3 of the Understanding Organic Chemistry 1 book. But we're going to be given a name and asked to draw the representation of that name. And remember what we said about pyranose? Are you going to be surprised at the end when the ring size is 6? I hope not. There's the end. Ring size is 6. Same for this one. Ring size is 6 over here, and a practice problem where it says furanose at the end. Are you surprised the ring size is 5? I hope not. And we'll go through all the steps right after we take a break. And the first step involves finding the right sugar from this name, and the sugar is embedded right there, and I will leave it at that. And see you very shortly.